Okay, let's go through problem 101. This is definitely the hardest problem we've done yet this year, and it's the hardest problem in this section for sure. So let's look at this these blocks, and we're trying to answer. This one has a weight of 16 kilograms. This one has a weight of 8 kilograms, and there's some friction on the ramp as well. Of the coefficient of friction is 0.23, and we're trying to find the acceleration of the blocks together because they're going to move this way, and we're trying to find the tension in the string. So what we can do to find the acceleration of the blocks is we can imagine that we're going to draw a free body diagram on the net force, basically. So we're going to imagine that these blocks are just like together. Just one. We're going to imagine that this is the system right now. We're going to picture the system and analyze the forces that are on the system. We have one force pulling downwards, and that's mg from this block, which if you do the mass of 16 times 9.8, you get, so there's 156.8 newtons pulling downward on this block. So I'm going to draw that going to the right on this one, 156.8 newtons. And then on the left, I'm going to draw these forces now. So I'm going to have to look at this box right here and try to analyze it. I've got weight pulling downwards of mg, so it'd be 8 times 9.8, which gives you 78.4. Okay. Now there's a component of that that pulls down the ramp. I'll call that f of x. There's a component that pulls against the ramp. I'll call that f of y, to give it a name. Now if this angle is a 37-degree angle right here, so this angle right here is going to be 53. And if you're not sure why, you can picture a triangle like this. Let me see. Let me use a different color. I'll use, I guess, black. This triangle right here, if you picture it as a right triangle, if this is 37, this is supposed to be 53. With that little right triangle right there. So we know that this angle right there is 53. Okay, so we're going to use that to find f of y and f of x. So we'll do, for example, sine of 53 equals opposite over hypotenuse. So sine of 53 equals opposite, that'd be f of y, over hypotenuse, 78.4. Multiply both sides by 78.4, and you get what this force is right here, which is, so this is 62.6, and that's pulling the box into the ramp. Now there's also a normal force that I'll draw right here, do a different color. That's going to be equal and opposite to that. So this is the normal force. And obviously that normal force is 62.6 newtons because it has to equal out this force right here so that the box doesn't move at all this way. It's only moving this way along the x direction. It's not moving in the y direction the way that I've called. I'm reassigning my axes as this is x and this is y on the box. So it's only moving this way. It's not moving up or down into the ramp. So therefore the normal force has to equal this y component of the weight. Okay. Now the x component of the weight, I'll do cosine of 53 equals adjacent over hypotenuse, so it'll be f of x over 78.4. I'll multiply both sides by 78.4, and I get the x component of weight is 47.2. So this right here would be 47.2 newtons pulling the box down the ramp. Okay, so now I've got, I know I've got the 47.2 pulling the system back the other direction, right? So I've only got one direction. I'll call this positive and I'll call this negative. So I'll call right positive and left negative for the system now. And that's what this free body diagram is up here. I've got one force pulling it to the right, or down, whatever you want to say. We'll say to the right, which is 156.8. And then I've got one force pulling back at 47.2. I've got another force pulling back, which is the force of friction. Okay? The force of friction is equal to mu sub k times the normal force, which mu sub k times the normal force, the coefficient of kinetic friction is 0.23, and the normal force is 62.6. So that gives me a force of friction. If I multiply 0.23 times 62.6, I get 14.4 approximately newtons. So I could have drawn that smaller because it's not as big. But the force of friction is about 14.4 newtons. That's also going to act to the left to slow this box down. So now I can look at this and do the net force. So the net force is equal to the big force, 156.8, which I'll call that the weight, so I'll do that N2G because that's the weight from the second box, but really that is 156.8. And I'm going to subtract the two smaller forces, which the two smaller forces were the x component of weight from this diagram, pulling back this way, which that is, that's 47.2. And then also we have the force of friction pulling the system back the other way, which is 14.4. Okay? And the net force now is mass 1. So really I'll write this as mass 1 plus mass 2 times acceleration, because every force is mass times acceleration. So F equals ma, but the net force in the system is both the masses times the acceleration. So what I'll do is I'll add both the masses, that gives me 24, 16 plus 8, times the acceleration, and I'll solve for the acceleration, so I'll divide both sides by 24. The acceleration equals, so the answer is 3.97 meters per second squared, which we can round to 4 if we're going to pay attention to significant digits. So the acceleration is going to be 4 meters per second to the right. Okay, that's for part A. So now for part B says what is the tension and the strain connecting the blocks. So now for part B, what I'm going to do is I'm going to look at block 1. So I'll call this block 1 right here. And I'm going to draw a free body diagram on that block, because I know on that block I've got the forces acting on it I've got a frictional force, I've got the x component of the weight that's pulling back on this block, and I also have a frictional force pulling back on this block. And then pulling it forward, if I'm just looking at this box, not the system, if I'm just looking at this one, then pulling it forward, I have a tension force. And I know that tension force is bigger than these two because I know there's a net acceleration this way of 4 meters per second squared. So when I do now the net force on box 1, so keep in mind this is on box 1, this is not for the system anymore. Now I'm just looking at this box and drawing a free body diagram for this box. You get, I'm going to do the bigger force, so it would be tension, subtract the two smaller ones, I'm going to subtract the frictional force and the x component of weight. Now the net force is mass times acceleration. I know the acceleration is 4. I'm going to plug in 4 for acceleration, or 3.97. And then the mass of this box I know is 8. The force of tension I don't know, that's what I'm trying to find. The force of friction I do know, that was 0.23 times the normal force, so that ended up being 14.4 newtons. Minus the x component of the weight, which was right here, which turned into 42.2. Alright, now I should be able to add these numbers right here to the other side, add it with 32. And that should give me the right answer for tension. And the force of tension should be, actually this should have been a 47, whoops, not a 42. Not reading my handwriting correctly. And technically this is 3.97 according to our calculations. And if you do that and solve for the tension, I get 93.36, which if you round, you can get the book has 93 for their solution because they round down for significant digits. So 93 newtons is the tension force that's pulling on the blocks. And you could have done this for block 2 as well. You didn't have to look at block 1. You could have looked at block 2. But either way, this is what you get for tension.